Okay, now for doubling the angle on the bow. Now the bow is the front of a ship or a vessel, the stern's the back, the port's on the left hand side, the starboard's on the right hand side. This method is used generally to determine how far a vessel is from an object, for example, an object along the coast. If we think about the parts of a ship, the bow here and the bowsprit is what the captain or navigator might use to help line up objects on the shore, and he might stand just around a compass rose, as we can see, for example, over here, which would help give the bearings. So let's think about this in more detail. The front of the boat is known as a bow. The angle on the bow is the angle between the boat's course and the bearing of the prominent feature. Now this is quite different to what we've been doing before, because we're using the angle from the boat's course and the bearing of the prominent feature, rather than using a true bearing, which, remember, with true bearings the 0 degrees is always facing north. This time we're lining up our protractor between the boat's course and the bearing of the prominent feature. We'll have a look at that in a minute. So the doubling the angle on the bow method uses the properties of isosceles triangles, which have a pair of sides equal and the base angles are equal. So if we have a look here, when angle A has doubled to 2A, the distance from B to C is the same as distance from A to B, and we're going to be using this properties for this process. So a couple of skills we just need to be remembering: that angles on a straight line add up to 180 degrees, so they're supplementary angles there. The three interior angles of a triangle add up to 180 degrees, and the isosceles triangles, generally the base angles on isosceles triangles are equal, and therefore we have the pair of sides which are equal. We have a look at a couple of problems. So if we have a look at problem A, we need to find the value of angle x, and we know it's a straight line, so there's 180 degrees on a straight line, and the value opposite x is 30. So we just say 180 degrees minus 30 should give you 150 degrees, and so x will equal 150 degrees. For problem B, we know there's 180 degrees in a triangle, and the other two add up to 100 degrees, so we just say 180 degrees minus 100 degrees will give you 80 degrees. With problem C, we notice that we have a pair of sides which are equal, and we need to find the angle which is not at the base. So we can consider that this one here should be 35, and so 35 and 35 should equal 70 degrees, and there's 180 degrees in a triangle, so we just say 180 minus 70 degrees to equal 110 degrees. If we have a look at this one, where it's getting a little bit more like our problems we'll see soon. So we want to find the angles A, B and C and the length of PR. So we can see that we have a pair of sides that are equal, so angle A must be the same as 40 degrees using the isosceles rule. Angle B must just be 180, take 40, so 140 degrees. And then angle C, well, we know that the angles inside of a triangle equal 180 degrees, and we know that we've got 40 plus 40 making 80 degrees, so angle C has just got to be 180, take away 80 for 100 degrees. And we know also then with side length of PR, it's got to be the same as PQ, and PQ is given, so that's quite easy. It's just 3 nautical miles. Now we're starting to look at the idea of doubling the angle on the bow and how these properties of isosceles triangles relate to navigation. Now, the usefulness of doubling the angle on the bow is finding the distance a vessel is from an object. So we've got a ship's course here, and you can see that it's heading due east, 90 degrees. But we're not looking at a true bearing when we're considering the difference between the ship's course and the lighthouse. What's important here is the 35 degrees. So we can see that there's a difference of a bearing of 35 degrees from the ship's course to the lighthouse. What we're going to now move on to the second picture. As you can see, when the angle has doubled, so 35 now becomes 70 at the front of the ship, we can note that the length of PQ, that line, should be the same length as that line. So if you know your speed and know the time, you can work out the distance, and then using that you can figure out the distance the vessel is at point Q from the object on the shore. Here's another couple of examples. So starting off with point P, so it's 30 degrees between the ship's course and the object on shore. So 30 degrees, when the bearing has doubled from the ship's course to the object on shore, we know that this line here and this line here, the distance that you have travelled has got to be equal to the distance to the object on shore. Let's look at the second picture. We've got the same idea, but we're just travelling in due east again. So here's our front of the vessel, 45 degrees from the front of the ship to the lighthouse. Now double 45 is 90 degrees. So we've got the same distance that you have travelled as it is to the object on shore. So let's have a look at a problem. Let's have a look here. We've got a ship or a vessel at position P. I've just marked it at the front of the bow, and we want to take the bearing from the ship's course to the control tower. We're just going to call that position A. So there's the front of the ship to the control tower, and the black line is showing, well, that's our direction of travel. So let's measure that. So remember, the protractor is not facing due north this time, so that's the first time we're changing that. We measure that angle between the bearing and the course, and in this case it's 40 degrees. Now the ship has moved along. It's moved up here somewhere, and by the time it has doubled to 80, there we go, there's our 80 at position Q. The distance from P to Q is the same as the distance from Q to A. So the distance you have travelled is the same as the distance to shore. That is, this one and this one are the same.